Okay, let us start. So yeah, as I said last time that we will have this as the last session for now. We may take a break for a few weeks, and in the meanwhile, I'll give you some ideas that how you can continue to work on your own studying for Olympiad or whatever you want to do. As I guess next Sunday is the INMO exam for some of you, so all the best for that also. And for everybody else who has not been selected for INMO, you can still attempt the paper later on and see how you are doing. And I mean, again, just to get your own judgment that what kind of questions are being asked and how you are able to approach it. Don't go with the assumption that because you did not get selected, you will find the paper tough necessarily. Some of the questions, at least you can give some decent attempt to try, even if you are not able to solve the question as so. Please give it a sincere attempt. Uh, so what I want to complete the kind of the topic of transformations with complex numbers today. So already we started to do this last time. We looked at a couple of problems where we could apply complex numbers, but there was one question from APMO which I shared last time, which I think that we can use that. I mean, that is a very good problem to develop a lot of theory of complex numbers. That how what are the various small results that you need to be prepared in advance so that if you want to apply a complex number in an actual exam and you do it efficiently, these small lemmas will be very helpful to you. So, okay, so that is why I think today's lecture will be very useful for that. By the way, in that problem, I have been trying with pure geometry for a long time, but at least I have not made any progress. I don't know if anybody else been able to solve that problem with only pure geometry.
Solo strike.
केलंच नाही का?
Anybody? No. Okay. So then that is why, I mean, that is why complex numbers can be very powerful. That once you see the
एक
solution of
दिवसाचा
complex
आहे.
number,
हा.
ते पण कॉम्प्लेक्स नंबर सोडवायचा होता कुणी ट्राय केला का तुमच्या
sorry, काय म्हणता हो?
नो सर
Ah, aha, नाही, शंभर वाटलं काय म्हणालास. Okay, so let us see that what is the sort of building blocks of the complex numbers that will help us to solve the problems. So to begin with, of course, we know that we can associate every point in the plane with its complex coordinate, which we denote by small p. Some useful properties or a sort of I don't know formulae from other like coordinate geometry. Like for example, I guess you might be aware of section formula. So section formula allows us to, if I have 2 points in the coordinate plane, and then the whole line can be described by just adding the 2 points in some ratio, right? So if the PQ are some points and some another point Z is there on that line. So it just as in coordinate geometry, you can take the ratio of the 2 points P and Q. You can do something very similar in complex also. So if we know these distances or the ratio is lambda and 1 minus lambda, then you can easily write Z is equal to lambda times Q plus 1 minus lambda times P upon, I mean, lambda plus 1 minus lambda, which is 1. So when the denominator can be ignored. So this kind of interpolation of between 2 points is possible. And of course, in special cases like when the z is the midpoint, so then obviously the coordinate of the midpoint is simply p plus q by 2, right? It's just the average of the two endpoints. And so combining these two ideas together, for example, in a triangle, when you have the points such as the centroid, right? So if I consider triangle ABC, what will be the coordinate of the centroid G? Can anybody tell?
Sum of coordinates by 3.
Yeah, it is the average of all the three, right? And if you want to, you can do it that way by because the m will be p plus c by 2. And now on this median, if you apply the section formula with the ratio 2 is to 1, you will get the centroid is actually the average of all of the three. Okay. And in fact, every point in the plane can be represented. So if I have a triangle ABC, right, and any point in the plane, maybe inside, maybe outside. So the coordinate of that point can be represented as alpha times A plus beta times B plus gamma times C, where alpha, beta, gamma are real numbers, such that their sum is 1. Okay, so as the position of the point P changes, the values of alpha, beta, gamma will change. Like for example, here you notice that G can be written as 1 by 3 A plus 1 by 3 B plus 1 by 3 C. So in other words, for G, the values of alpha, beta, gamma are all 1 by 3. But so every point in the plane has this triplet of values. So there is a whole theory related around this. So these are called barycentric coordinates. Okay. And you can find the barycentric coordinate expression for different points. So the centroid is special in that the values 1 by 3, 1 by 3, 1 by 3 are fixed, no matter which triangle you choose. But for some other points like the orthocenter, circumcenter, those alpha, beta, gamma themselves will depend on the angles of your triangle and things like that. So there is some dependency there. But all of these special points in the plane have this kind of barycentric coordinates, and you can do a lot of geometry with these barycentric coordinates. Like if you have 2 points P and Q, something very interesting happens is that the barycentric coordinates can also be interpolated just like with section formula. So if point P has coordinates alpha 1, beta 1, gamma 1, and Q has coordinates alpha 2, beta 2, gamma 2, then all the points on this line can also be interpolated with the same kind of section formula kind of result. Okay, so there are lots of interesting applications of this. Actually, this is a full topic which needs some dedicated discussion, which right now will be a bit of a distraction for us, but you can take this as a homework that try to read up about barycentric coordinates as much as possible and how to apply that. Okay. Then apart from that, in the standard theory of like when we are still dealing with triangles, right? Like if you want to apply complex numbers to triangles, one very useful thing that is done is that we choose the because we are free to orient the triangle in the plane anyhow we want. So often what people like to do is choose the circumcenter as the origin. Okay. And going further, somebody can also choose the circumradius as one. Okay, so basically what we are saying is that the triangle ABC is inscribed in the standard unit circle, right? So the origin O has the coordinate 0 and the radius of my circle is 1. Like in general, in most questions, you can just scale the triangle up, the diagram up and down to achieve this. Okay. So as a result, what happens is that so all these points ABC lie on that circle of radius 1. Okay, and now in this context, we can find the coordinates of some, I mean, complex coordinates of some very nice points. So, for example, firstly, what the midpoint of BC, that will still be B plus C by 2. So, nothing changes about that. But now, if you notice, so this is represented by this vector, you can say that from the origin to this point M. And so, if I know this, what can I say about the orthocenter? What will the coordinate of the orthocenter be? Because we know AH is parallel to OM, right? So whatever is the vector OM, AH will be twice of that.
A plus B plus C.
Yes, it is A plus B plus C, right? Why? Because basically what I can say, the coordinate of H, right? If I call it a small h, is equal to A plus H minus A. And in this A plus H minus A itself will be 2 times M. M minus O. M minus O means basically M minus 0. Actually, O and 0 are going to look the same, but doesn't matter. So, okay. So the fact that AH is parallel to AH is parallel to OM and AH is 2 times OM can be captured in the way of complex coordinate in this way, right? That the vector AH is twice of OM. So if I substitute this over here, I'm going to get A plus B plus C by 2 into 2. So that is A plus B plus C. So you see that's very interesting that if you choose the circumcenter as the origin, then the radius did not matter in this case. So it is just about the circumcenter being the origin. That is why H is equal to A plus B plus C. can you derive this from another way? Because we already found the centroid is a plus b plus c by 3, right? So centroid is already a plus b plus c by 3. So do you see that will also lead to the fact that orthocenter has this coordinate? Because we know the ratio between OGH, right? On the Euler line, we all know that wherever G is located, and if you think of it, it is like a dilation of the ratio 3 is to 1. So if G has this coordinate, H will be 3 times far away, and therefore H will have this coordinate. And so, in fact, you can also find the coordinate of the 9-point center will be simply the midpoint of ON, right? So midpoint of ON is H by 2. So, so all of these points will have nice coordinates because of the choice of the circumcenter as the origin. Okay? And many others. So, I mean, this is a very good frame of reference, choosing the circumcenter as the origin. Lots of calculations get simplified as a result. Okay. And we are going to make use of this in our problem also, that APMO question. Okay. But then moving on to some other useful lemmas, like which I think may be useful in some other context also. Like, for example, let us consider what happens when you reflect of a point in a line. Okay. So in general, if I have some point P, right, and some two other points Q and R, right? So what I want to do is I want to take the line QR and reflect the point P. Okay, so the reflection of the point P has some new coordinate. So I would like to know what is that complex coordinate of the reflection, if I call it S. So how can I relate P and S is the question. Okay. So instead of directly doing this problem, let us simplify the problem a little bit. Let us say that this line that we are considering passes through the origin, because that is very easy to obtain. You can just translate the whole diagram so that one of the points Q and R lines at the origin, right? So for now, assume that uh, the origin lies on the line. Okay, so therefore, I just modify the diagram a little bit. That so what I have is the origin of my coordinate system, and I'm talking about a line passing through that. Okay, so let us say on that line I have some point Q. Okay, and now some other point P has to be reflected. Okay, so I'll give you some time to think that how will you compute the coordinate of this reflected point. So what do we know? Do we know how to reflect the point in the x-axis? What will be the reflection of the point P? Let us say we want to reflect the point P in the x-axis. What will the coordinate of the reflected point be?
P bar.
P bar, right? The P conjugate, right? So this is P conjugate or P bar. Okay. So then we have to think that is there any connection between this P bar and the actual reflection that we want? Like if I just mark some angles over here. Let us say this angle, this line is inclined to our x-axis, whether it's an angle alpha. Okay. And P itself makes some different angle beta. Okay, so because of the reflection, the same angle beta will get copied over here. And what can you tell me that finally this line, the point S that we want, can we compute any angle related to that? Which angles can we compute here?
Okay, we can compute like x-axis and OS angle.
Okay, yes, correct. So we in this diagram we can clearly see that angle POQ is beta minus alpha, right? And because of OQ is the line of reflection, so therefore this will also be equal to angle SOQ, right? Or let me write as angle QOS is also beta minus alpha. QOS, okay. And out of that, if I subtract this angle made with the positive x-axis, temporarily let me call this point x. Okay. So QOS is nothing but QOX plus angle XO, right? And out of that, this is alpha plus angle XOS, and that is equal to beta minus alpha. So therefore, angle XOS is beta minus 2 alpha. So therefore, what about angle SOP? How much is angle SOP?
2 beta minus 2 alpha.
No, no. This what we got is SO. This angle is beta minus 2 alpha. My pen is not working, right? And this whole angle is beta. So how much will this angle be? It's 2 alpha, right?
Yes.
Okay. There is one more way to see the same thing, but I mean, just to complete the calculation, this is 2 alpha. And by the way, everything is from the point O, the distances are not changed. So OP, all of these are same. So if you look at a triangle, SOP is an isosceles triangle. So triangle SOP is isosceles with the angle at this angle at the top. Angle SOP is this much, 2 alpha. So now I have to think that what is uh, the complex operation I can do on this P bar to make it coincide with S. It is a rotation of angle 2 alpha, correct? So therefore I can say that S Right now it is maybe not a very nice way to say, but S is going to be P bar into cis 2 alpha, right? Because cos theta plus sin theta of 2 alpha will apply the rotation. But this cis 2 alpha depends on knowing the value of the angle alpha. And I mean, from the point Q, I can get the alpha as the, that tan of the real and imaginary part. But it would be nice to get this expression in more cleaner way. So we can do that by, if I take the reflection of point Q also, let me take the reflection of point Q, so which is Q bar. Then do you observe something about this point Q bar? Q bar, O and Q also form the same triangle. You see, that is also an isosceles triangle with the top angle as 2 alpha, right? This whole angle is 2 alpha. So exploiting the fact that this triangle and the other triangle, they are similar. So therefore I can say that, see, whatever operation is required to go from so going from small p bar to s, whatever operation we are going to do over here, the same operation is responsible to go from q bar to q. So whatever is the factor of multiplication, it's the same, right? Because the triangles are similar. And so clearly in this case, what is the factor of multiplication? It is simply q upon q bar, right? If I multiply the first term by this expression q upon q bar, I'm going to get the second term. So therefore, if I use the same term to multiply p bar, I should get s. So in fact, s is nothing but p bar times q upon q bar. So that is the final expression of the reflection. Okay. Just to explain this in one more way, that you could observe the same thing by using geometric transformation, because uh, here is how I describe it. See, in this diagram, use a different color. See, in this diagram, what are we doing? We are reflecting point P in the this line first, okay? In the positive x-axis, that is the giving me one reflection point here. Let me call it P1, okay? And we are also reflecting the same point P in the this other line, which is giving me a different point. Let us say P2. So we are asking what is the relation between P1 and P2. When the, like, basically you can think of these are two mirrors and the angle between the mirrors is alpha. So what we are saying is that when the mirror itself rotates by an angle of alpha, the reflection rotates by angle of 2 alpha, right? So this angle of rotation of the reflection is 2 times the angle between the mirrors. And you may have seen this principle in some other cases also. In real life also you can see that if you are standing in front of a mirror and if you rotate that mirror 30 degrees, your reflection will seem to rotate 60 degrees. Okay, you may have seen this effect. So that is what is happening here. So that is why the relation between P2 and P1 is 2 alpha, the rotation of 2 alpha, when the angle between the lines of reflection is alpha. That is what we are basically applying here. Okay, so this is the expression if that line of reflection is conveniently passing through the origin. But if it is not passing through the origin, like what we did earlier, we can always translate the whole diagram to make it pass through the origin, right? So here basically you can think of this O as doing the job of R in the diagram above. Like if I want to take this diagram into this diagram, I just have to take the point R and place it at the origin. So translate the whole diagram, make R at the origin, do the reflection, and then translate it back to the original position, right? We do this all the time. So if we do that in this diagram, can I, maybe I'll just give a minute to write what will be the coordinate of S in this general situation. how do we do that? Let us do it step by step. So let us say first step we do what I said. Let us translate the whole diagram so that R coincide with the origin. So when we do that translation in the new diagram, what will happen? The R is replaced with the origin, and everything else will have some offset at it. Right? So Q will be replaced by a point with coordinate Q minus R. P will be replaced by a point whose coordinate is P minus R, and S will be replaced by a point which coordinate S minus R, right? And so in this situation, we know how to relate the coordinate of this reflection with the original point, right? So like applying this expression over here, what I can write is S minus R is equal to the original point P minus R conjugate into Q minus R upon Q minus R bar. Right, that is what in the translated version it is going to be. And so here, because I'm using this S as the original point, so I just need to rearrange this. So if I rearrange this, what will it look like? I can write this as S is equal to R plus, I mean, it is not much of a rearrangement. I'm just taking the conjugate sides to one side. Okay. Yeah, just to understand this expression, maybe at the moment it looks like a very complicated expression. So we looking at the expression, it is not maybe giving us any confidence that why will this be the right expression? Just because maybe we did some calculation mistake, we don't know, right? So let us interpret this equation in a slightly different way, which will give us the confidence that okay, this equation can really be true. Okay, so let me just draw that diagram separately over here. So again, we are talking about the same 4 points, nothing is different. So Q, R, P, and S, right? And what the equation we got finally is S is equal to R plus that P bar minus R bar into Q minus R. This is the expression that we got. And as I said that looking at this, it is not really clear at all that why this will be true. So let me just rearrange it a little bit. So let me take R on the other side. So I'll get S minus R is equal to everything else. And let me take, what can I take? Let me take this Q minus R term on the other side also. I'm going to write it like this. S minus R upon Q minus R is equal to P bar minus R bar upon Q bar minus R bar. So I've taken all the conjugate kind of terms on the one side and I kept everything else on the other side. Okay, and as you know that conjugation can be easily taken in and out. It distributes very well over all the standard operations. So this can be written as conjugate of this whole bracket. Okay. Still, why does this expression make sense? Like looking at the first term and the last term, why will they be equal? Is there any way of thinking of this in some other way to make it clear? So we understand what is the meaning of conjugation, right? Conjugation is a reflection in the x-axis, the positive x-axis. So let me in the diagram, let us say that a positive x-axis is here. Okay. In fact, I mean, forget the conjugation part. Let us look at this interpretation only. So here, let us say every point I reflect in the x-axis. If I reflect my whole diagram in the x-axis, I will get a diagram like this, right? So this the R bar will be here, uh, Q bar will be here, and P bar will be here. Okay. So by geometry, do you agree that triangle in the original reflection, what happens is triangle PQR is congruent to triangle SQR, but the orientation is flipped, right? It is the if PQR are anti-clockwise, SQR are clockwise. But if I reflect the triangle PQR, so if you notice, because I am reflecting PQR all the three in the x-axis, so PQR is congruent to triangle P bar, Q bar, R bar, and again the orientation is flipped again. So if the same triangle PQR is congruent to both the triangles with opposite orientation, with actually what it means that these two triangles are congruent with similar orientation, and we see that right in this diagram, triangle SQR and triangle this triangle, they are both congruent and the orientation is also the same. And if that is the case, in fact, I mean, we only require similarity, we don't even require congruence. Okay, whenever we have two triangles like this, which have the same orientation and they are similar to each other, now can you interpret this expression? What is S minus R upon Q minus R? What is this expression saying? Can I interpret this expression as if I consider the vector RQ, right? By how much I need to rotate and scale it, like what is the spiral homothency I need to apply to make it coincide with RS. So that this angle of rotation and whatever is the ratio of these two sides. We all have still seen it many times by now that this kind of operation can be thought of as a spiral homothency. So whatever are the parameters, this alpha and the ratio K, those are captured in this expression. And if you look at the second expression, do you see that the same thing is being applied there for this diagram where now instead of QR, I mean other vector RQ, we are considering the vector uh, R bar Q bar. And again, we are asking the same question. By how much I need to rotate this vector alpha R bar Q bar to make it coincide with RP? Like what is the ratio? And because of this similarity, this alpha K have to match. And that is what means that these two expressions have to match, that this ratio is being compared. Or what is that factor of multiplication which will take RQ into RS or R bar Q bar into R bar P bar. So that is the reason why this is true, and therefore from this also you can back calculate and get the same expression. Okay, so just to give us some more confidence that this expression may look kind of very complicated, but it is actually making a lot of intuitive sense if you look at it in the geometric transformation way. Okay. So this was about reflecting a point. By the way, once you obtain the coordinate of the reflection, do you see that now it is very easy to find the coordinate of the foot of the altitude? Like suppose I wanted the coordinate of this foot of the altitude. What do I do?
Midpoint formula.
Yeah, it is just the midpoint of PS, right? If I found S and P, then T will be simply P plus S by 2, right? Some issue with my tablet today. Yeah, okay. So yeah, so you see indirectly when we found the reflection, we also found the coordinate of the foot of the perpendicular. Okay. So yeah, so this is like what I'm saying, that these kind of special properties, if you have all of these kind of very ready at your disposal and if you have to apply them in an exam problem, you can do it quickly. But for that, it is important to do this background work and keep all these things ready to save your time. Okay. So one last thing that we will do before we start looking at our problem is that uh, because what our problem demands at some point is that we want to find the circumcenter of a particular triangle. Okay. So again, if we have some points P, Q, and R, and I would like to find the coordinate of the circumcenter. Okay, if I call it C, I can don't want to call it O because we can confuse O with the origin. So I want to find the coordinate of the circumcenter for any 3 points. Okay, but again, this is a very difficult problem to directly attack. So let us just translate it and make the one of the points as the origin. Okay, let us solve that problem. So let again, same as before, let us say I conveniently choose the one of the vertices of my triangle as the origin. Okay, so now the triangle is located like this. Okay, and now I have to find the coordinate of my C. Let me take a acute angle looking triangle. Doesn't matter, finally the expression is the same, but just because we are familiar with that little bit more. Uh, Let us say this is my origin, and I want to find the coordinate of my circumcenter. So one very complicated way to kind of do it is that because we know the point P and O, we know the midpoint is P by 2 here, and the perpendicular bisector of that will be something. And similarly from here also there will be a perpendicular bisector from Q by 2, but we don't know that angle exactly. So we have to compute that. And more importantly, we don't know how much distance we have to travel along that vector. So that also we have to compute. So we have to do lots of computations that way to get the point C. So
Sir,
this is
we know like circumcenter is orthocenter of medial triangle.
circumcenter is the orthocenter of median triangle. That's a good point.
So like, oh, because don't have. Yeah, so we can use orthocenter for it.
Yes, but the thing is that orthocenter expression we got A plus B plus C, that is valid only when the origin of your diagram is at the circumcenter. So then you need to know the circumcenter of that medial triangle.
Yes.
And that may become like a chicken and egg problem that to find the circumcenter of one triangle, you need to know the circumcenter of another triangle. Okay, let me suggest a different approach. See what we always do, kind of that if we have one reference line, right? In this diagram, see, we understand the vector OQ very well. OQ is in our control. So I'm asking that how much I need to rotate or scale this OQ to make it equal to OC, right? So in this diagram, if I look at the vector OQ, and if I want to rotate and scale it and make it fit this OC. So if I can somehow work out what is this transformation required, what is the spiral homothency required to achieve this operation. And I mean, I can again do it in terms of angles. I can try to find this angle, try to find the ratio. But what complex numbers gives us the power is that if you have any looking at this shape, right? This triangle OCQ has a particular shape. If by my luck I can find some other triangle in the plane which has the exact same shape. Okay, and let me call this point some I don't know, Y and Z. Okay, so what complex number has given me the power to understand is that the same operation of going from Q to C will also go from Z to Y. So if I find these nice points Y and Z, I can directly write that C is simply going to be Q times Y upon Z. Like same thing what we did just a few minutes ago for the reflection point. So my only challenge is to find these nice points Y and Z which are similar to this triangle OC. So where, so now this is all about your ingenuity that where can you find these points Y and Z, which are similar to the OCQ. But you start to see that how often that spiral velocity idea is coming. The fact that multiplication in algebra is spiral velocity in geometric transformation. That is again and again it is applied everywhere. So if you have any doubts about that, that how are we doing this? Like maybe if somebody is not sure that how we are able to write this expression, go back and watch that part of the lecture. Okay. So what is the shape that we are looking for? Like it is an isosceles triangle, right? Firstly, we are looking for an isosceles triangle, and what are the angles of that triangle? Like let us use the, it is too much overloading the same letter. The point the P also represents the vertex, small p represents the complex coordinate, and now I'm saying capital P also represents the angle. But let it be. So if this angle is P, this is going to be 2P, right? This central angle. And what about the angles on the side? How much will they be? 90 minus P, right? So this is 90 minus P. This is also 90 minus P. So where how will I get this angle 2P? We just did this few minutes ago. This angle 2P is there somewhere. So maybe it is difficult to spot this at first, but what if I reflect the point O, the origin, in line PQ? Where will it go? I just found the expression of how to reflect one point in one line, right? So I want to use that right away. Why will I wait for something? So if I reflect the point O in my line PQ and it goes to some new point, uh, let me call it S. What can you say about this triangle? Isn't it the same triangle we're looking for? This triangle OSP has exactly the same dimension that we're looking for because this angle is P, this is an isosceles triangle. So like triangle OPS is similar to triangle OCQ. And so if I know the coordinate of S and P, so therefore, like instead of writing it this way, I can write C is equal to Q times instead of Y by Z, it is P by S. And so, I mean, I just to find the value of S, I can substitute the expression which we found just few minutes ago. It is the same expression, right? So let me just copy that expression. Okay, except that in that expression the PQS were slightly different. Uh, that's replace that accordingly. So in that diagram, my Q and R represented the 2 points in the on the line of reflection. So here instead of Q and R, I have to write P and Q, right? So I'll just use this reference. So this term has been replaced by P bar minus Q bar, and the actual point which I wanted to reflect, which was small p, but that is the origin. So this term will kind of go away. I don't have to write anything over there, and this R will be the same as Q. So the S will be equal to Q, thus. Okay, so this is your point S. So therefore, if you substitute this in my expression, I'll get C is equal to Q times. Before that, let us just clear this denominators and everything. Let us just simplify this little bit. Okay. And so here I think something is cancelling. So S is simply Q times P bar minus P times Q bar upon P bar minus Q bar. Okay. And you can keep doing this exercise that every time I get some complex number expression, I have to spend a minute looking back at the original diagram and understand what is it representing, because there will be some connection. Say complex numbers may look like a lot of algebra, but it is, I would always think of that as geometry expressed in algebraic form. So there is some underlying geometry also happening. If you understand that geometry happening, just as what we did for this reflection expression, right? Then it will make a lot of sense. Otherwise, it may be very mysterious that why is this happening. Okay, so finally the circumcenter that we're getting is Q times P into the reciprocal of this. Okay. Oh, no, sorry, I think this is. And again, in this expression, just to rewrite it a little bit to understand exactly what is this expression saying. Don't just accept it at face value, because it is saying something very important. If you look at the denominator, right? If you look at the denominator, there are two terms: Q times P bar minus P times Q bar. But those are conjugates of each other. Do you see that? So it is basically Q times P bar minus the conjugate of Q times P bar, because conjugate of conjugate becomes the original. So what can you say about this expression, the denominator? When you subtract a number from its own conjugate, what is the result?
2 times imaginary part.
Yes. So important thing is that this is a purely imaginary number. So for any complex number z, z minus z bar is purely imaginary. Okay. Because in the diagram also you can see that if this is z, this is z bar, then z minus z bar is this vector, right? So this is perfectly at 90 degrees. So it is a purely imaginary vector. So what that means in terms of direction, that if I consider consider the only the numerator part, right? So that represents some complex number in the plane, right? And what we are saying is that the denominator, which is a purely imaginary number, which means multiplying or dividing by the denominator is a 90-degree rotation. So the actual circumcenter, so if I call this as n, right? So if this point is somewhere over here of with this coordinate, the actual circumcenter will be at 90 degrees to that with respect to the origin. That is what this expression is saying. Or in other words, what we have discovered here is the equation for the tangent to that circumcircle. So if you plot this point, you are going to get the line of tangency at that vertex O. Okay, actually, let us see this in action. Okay, let us look at this expression PQ, P bar minus Q bar in GeoGebra to appreciate this fact that what we are really doing is so setup is that so one of the vertices we are considering is our uh, origin of our system. Then one point is P and other point is Q. Okay, and so we are interested in the circumcircle of triangle OPQ, right? Rather the circumcenter. I don't really care about the circle as such. Okay, so we are calling this point as C. Okay, and now in this diagram, I want to plot the point PQ into P bar minus Q bar. So how do I plot this point? So I can take what I'll take is let us plot P bar minus Q bar first. So for to get P bar minus Q bar, let me get P bar and Q bar. So let me reflect my points P and Q in the our this axis. So this P dash Q dash are the P bar Q bar, and now P bar minus Q bar means this we are talking about this vector. So this line O U this vector U represent this term P bar minus Q bar. Okay, so I need to multiply this vector with P and Q. So the product of all these three is what I'm interested in. Okay, and so to compose that product, and finally I'm only carrying out the direction. I don't care about the magnitude as such. So I am all I'm going to do is I'm going to take these angles. So let me just for reference take any point on the positive x-axis. So this is just my unit to represent the unit direction. So the first angle is POU. Oh, sorry. Okay. So this is the angle formed by P. Then this, which is alpha. Here it is maybe difficult to see. Okay, but it has given the names that this first angle is alpha, this second angle is beta, and the third angle, this P dash Q dash. Let me just translate that P dash Q dash at the origin, just to make it look easy, nicer. Okay, so this O dash. So that is the third angle. Yeah. Okay. So when I multiply these three complex numbers, the what we have seen this multiple times that the argument will get added, right? This angle will get added. So the product of all these three, P into Q into P bar minus Q bar, will have angle alpha plus beta plus gamma. So I can here just compute alpha plus beta plus gamma. Okay, so this delta, which is alpha plus beta plus gamma, is 122.67 degrees. And so what I expect as per the geometry is that this uh, direction is at 90 degrees with our circumcenter. So let us see. So if I let us say I rotate this point, my unit point around the origin with this angle delta. Okay, so this point U. And finally, I expect that this point U and my circumcenter are at 90 degrees. So let us see if that is happening. So yeah, you see how nicely it is. This, let's change it to a different color. So you see that orange colored angle, which is representing that direction. And now if I change the position of P and Q anyhow I want, but still that angle is remaining 90 degree always. So it is a nice, I mean, feeling that when the geometry and algebra match very nicely. Okay. And also this gives you some idea that looking at this expression, it may be so difficult to figure out how I'm going to convert this into geometry. But it is not that difficult because here, particularly because we are only caring about the direction. So we just have to add the angles of all the three vectors. But anyway, I mean, so the important thing is we have the equation for the circumcenter now. And so this was the case where we conveniently chose one of the vertices as the origin. But as what we already seen before also that it is not that big of a change. We are just doing a shift of origin. So we are going to get C is equal to, so P into Q into P bar minus Q bar upon, for that expression, QP bar. Okay, so this was the circumcenter of triangle OPQ. Okay, and so how to apply this to get the expression for the original PQR? That is, I will leave that as exercise for you. One thing that kind of interesting happens there is, at least when I tried this, I actually tried this, calculate this yesterday. Somewhere I got stuck. We expect that the answer has to be very nicely symmetric in PQR, right? So to make it symmetric, it requires some amount of trickery that maybe we have to add or subtract some nice term in the numerator denominator to adjust and factorize. Some adjustment may be required, but if you are able to do that and give you a nice symmetric expression for the circumcenter of PQR, I would very much be interested to look at that. Okay, but yeah, in principle, it is possible. Okay, so again, I'll just pause for a minute and make sure that you note down all these results, that the circumcenter of any triangle, the foot of the altitude from any point to any line, or the reflection of the any point in any line. So these are like small lemmas which if you have available in the same way after the lecture you can think about angle bisector, perpendicular bisector, those the equations of those. Okay, all those things, if you are ready available with you, it will save you a lot of time. Okay. So with all of this background preparation, we can start to think of the actual APMO problem. Okay, so let me rewrite the problem here. APMO. Sorry, it was 2010. So I'll just draw the diagram of the problem. So ABC standard configuration, which is the ortho center, and they are given that if you consider the circle ABH, let it meet the this side again. So given that points. Okay, so there are basically two cyclic quadrilaterals here, ANHB and AMH. Okay, I'll erase this circle, but just to illustrate. And so what you have to prove that, and if O is the circumcenter of triangle, the circumcenter of triangle MHMN lies on the line HO. Before we start by, like somebody may have the idea that let us just compute the points M and H, plug in the circle, that circumcenter formula we got, and somehow you have to get it on the line OH. So that is right, that is what we want to do. But before that, let us just discover the geometric properties that can be, right now what they have given this description of points M and N is a kind of very complicated that you have to go through the cyclic quadrilaterals to get them. But can you see that there is an alternate way of defining these points M and N also? Is there any alternate description of the same points? Like let us focus on point M, for example, and let me erase the circles. We know that which cyclic quadrilaterals we are talking about. So let us look at only point M in this diagram. Okay. So if I just, instead of drawing the circles, if I join the lines, then I expect this to be a cyclic quadrilateral. So can I, which angles can I compute? Like how much is angle AMH going to be?
+90.
It is 90 plus A because it is 180 minus the opposite angle ACH, and ACH we know is that if I continue this, here this is 90 minus A, so this is 180 minus, so 90 plus A. So AMH is 90 plus A. So what can I say about this remaining angle? BMH. BMH is 90 minus A, right? So if this angle is 90 minus A, that my pen is not working properly. Does that suggest that there is some other way to describe the point M? Can I have some other way of defining the point M? Where do you see this angle 90 minus A in the diagram? Anywhere else?
Like M is reflection of B about CH.
Yes. If you look at this angle, you also 90 minus A. And so, I mean, clearly in this diagram, you will see that this line CH is going to be the line of symmetry for which B and M will be reflections. So therefore, M is the reflection of B in line CH. So you see, this is an alternate and hopefully easier way to describe the point M instead of going through a cyclic quadrilateral. And the same thing can be said for the point N also. So for the point N, if I drop this altitude and take the reflection, maybe in the diagram it will go a little bit outside that segment, but that's okay. Maybe somewhere over here, this is point N. So in the same way, I can say N is also the reflection of C in the line BH. And so you see how what we had computed earlier, we had that is why we do those two lemmas I did in particular. So one is the if I know the coordinate of H and C, then I can find the coordinate of M. And similarly, I can find the coordinate of N also, applying those formulae. Okay, that is not all. I mean, at this point, we may probably have enough data to start with the complex number crunching. But just to complete the picture, that this point M is also special in one more way because we know something very important. If I consider the circumcircle of ABC, right? If I extend this line H, right? We know that where it meets the circle again, right? If I call that point some Z, okay? So Z is the point where the basically the point of reflection of H. Then do you see that actually what I'm going to get is a rhombus? This is a rhombus, right? BZHM is a rhombus. Or I mean, it is enough to observe that it's a parallelogram. So actually this vector HM, right, is equivalent parallel to BZ. So BZ is equivalent parallel to HM. So that could be one more way to find the coordinate of point M. If I know the vector Bz, I can apply the same to point H. The translation from point H will give me M also. So that would be one more way of obtaining the point. So yeah, there are multiple ways to reach the point M. Okay. So see why complex numbers are so popular among students is that you don't have to do any special construction. I have not seen the official solution of this question, but I am very sure that if you want to do this with pure geometry, you have to think of some clever idea that some new point has to be introduced in the plane, and if you use that point, something gets simplified. But not everybody will be able to think of that in the real time, 30 minutes, 45-minute time limit. But complex number does not impose any restriction of that kind. It is simply number crunching. Of course, you have to be efficient in doing that. And today we are going to see that how you are supposed to choose the right frame of reference to reduce the calculation, but essentially it is just number crunching of some kind. Okay. So that is the beauty of the complex numbers. Okay. So let us try to compute it. And so now the most important part, that choosing the right frame of reference. This is where the whole problem gets solved or unsolved, I'll say. I mean, you may not understand at front that why this is important. If you just call the points a, small b, small c and do it, of course you can get it, but the calculation will simply go out of control. So we are going to exploit the maximum freedom that is given to us. That like we are free to choose, as we said earlier, that uh, circumcenter of ABC. First thing I want to do is choose the circumcenter of as the origin. That is the first thing we are going to do. Because of that, what will happen? The our H will have very nice coordinate at A plus B plus C, which we are going to care about a lot. Not only that, I will also choose the circumradius of triangle ABC as 1. And why is that important? Because what that means is that the magnitude of my all the three vectors, right? Mod A, mod B, mod C, they're all equal to 1. The magnitudes of all my any point on the circumcircle is at a distance of 1 from the origin. So that is going to be very important. Okay. And not only that, actually there is one very important property about these kind of numbers, which we have not talked about before. If you look at any point on the unit circle, right? Just to quickly talk about this. So if you have any point Z over here, so its image, we know what is Z bar, right? This is Z bar. But you'll observe that Z bar is actually same as 1 upon Z. So wherever you get Z bar, you can replace it with 1 upon Z. And why is that too? Because basically what is happening here, see these angles are obviously of opposite sign. If this is plus 30, this is minus 30. But the magnitude of the two vectors is also same. So therefore, if you want to, if this is if you represent this as polar coordinate system, this is basically one cis alpha maybe, and this is one cis minus alpha. So when you multiply them together, we know the magnitudes get multiplied, so that remains one. So the product of these two will be simply one cis of alpha minus alpha, which is one cis zero, which is one. Okay, so this fact that conjugates and reciprocals are the same thing if you are on the standard unit circle. That is a very important thing which will help us a lot, because we are going to do lots of reflections. So we'll all the conjugate terms we are going to come in the expression, but we can simply replace that with the reciprocal. So the fact that A bar is simply 1 by A, B bar is 1 by B, C bar is 1 by C. So all of these are going to help us. Okay, so that is why this is also very important choice. But that is not all. Can we do something more? We still have one more degree of freedom available with us to simplify the calculation even further. Can anybody think that what is the one more step that we can do to make our life even more simple?
Like the direction of the axes.
Yes, correct. So can I conveniently rotate my whole diagram so that choose point A with the coordinate 1 comma 0. Okay. So that my small a is simply 1. The coordinate of my point A is simply 1. I am free to do that. I can rotate my whole diagram so that O is my circumcenter and A is my unit point. So these are all the three things I'm going to do, and you will see that how this is going to make this calculation very much feasible. Okay. So with all of these things added, so therefore now the first thing is that the orthocenter is simply 1 plus B plus C, correct? Because it was A plus B plus C earlier, but now A is replaced by 1. So you got the orthocenter. Then then we we want to get the coordinate of the point M, right? And to do that, it is simply the reflection in the line CH, right? So we can apply the formula directly to get the coordinate of the point M. So M will be equal to, so I mean, I don't have the formula by heart. I'll have to copy it from somewhere. Actually, it is worth thinking a little bit that how can you develop some clever trick to make this formula easy to remember? Maybe changing the this PQRS is not maybe that friendly. Using some other letters, how to make this formula easy to remember. That is something as an open exercise for us. Especially for those of us who are like impressed by complex number, that we really think that yes, complex number is the best thing ever. Then you really have to spend a lot of effort to become efficient at remembering these formulae. If somebody is not that impressed by complex numbers, of course, you can go in a different direction. Maybe you like trigonometry, maybe you like coordinate geometry, or maybe you like pure geometry. You know, the way we say that only angle chasing ratios, only that is pure geometry. But I mean, it is somewhat an arbitrary distinction. It is nothing like that actually. So here in this, if I say that, so the P, the point which I wanted to reflect is B in my diagram, and the points Q and R, which I have from the line, can be replaced by C and H. Okay, so accordingly, I'll make the substitution. Okay, and H itself can be replaced by 1 plus B plus C. So this is equal to, and let me keep it as H only. There is a point. See, that is the reason why I want to keep H as it is, because finally we care about the triangle HMN, right? So triangle HMN, I can sort of make H as the center of my all my operations. So I'm going to use H as the point of reference. So therefore, I'm going to keep the H plus term as it is. Okay? I will not expand that, but everything else can be expanded. Okay. And see again how the fact that I chose my A as the one, so one is its own conjugate, so I don't have to write the conjugate of that every time. Till that minus sign will cancel one more time. Okay, so I obtained something like this. So let me think, can we simplify this further? So now at this point, see this B bar and C bar, as we said earlier, we can replace them with the reciprocals, right? So I can also write this as 1 plus 1 upon C into 1 by B, 1 plus B upon 1 plus 1 upon B. So that will give me further ways to simplify, because if you see now here, 1 plus 1 upon B can be rearranged as simply B, it is simply B, right? So M is turning out to be simply H minus 1 plus 1 by C into B. And in a very similar way, if you because the whole diagram is symmetric with respect to B and C. If I exchange B and C, this point M, whatever it was doing, the same thing will be true for point N also, right? It is just a mirror image of that. So I can directly write the expression for point N as H minus 1 plus 1 upon B times C. Okay. So now I want to focus on just the triangle M and H. So I can ignore everything else in my diagram and just look at this triangle M, N, H, and for which I know the coordinates of all 3 points. And then I'm interested in the coordinate of its circumcenter. So let me call the circumcenter of this as what, O1. Okay. So I'm interested to show that O1 and H are collinear. Okay. And where H is already, I know, is 1 plus B plus C. And you see how I represent M and N also in terms of offset from H. So actually, if you look at this, these terms are representing these vectors, right? So, I mean, uh, what if I can translate my whole diagram, because I have found the formula for a circumcenter when one of the points vertices is at the origin, right? But here HMN, none of them are at the origin. But I can, you see, I can free to translate my diagram so that instead of considering these points M, N, and H, what about if I consider the translation of this whole triangle, right? If I use this vector HO to translate this whole triangle here like this. So these, if I want to consider this triangle, it doesn't change anything. If this point O1 was going to lie on this line OH initially, it is continuing to lie on that. So O1 dash, the circumcenter of this new triangle also going to be the same. So I can simply replace. So I want to simply replace M, which is H minus this, by, I'm just going to drop this H term entirely as if it never existed. Okay, so I'm going to consider this as my new M. I mean, I can call it M dash or whatever, but just to avoid the writing dash every time, I'm just going to start treating this as my new point M. And in the same way, I'm going to completely replace my other term also by completely dropping the term. Okay. Not only that, I can go one step further. This minus sign is also not required, because if you think of it, if I again apply this operation, if I rotate my triangle 180 degrees, okay, so M dash will become minus M dash somewhere over here, and N dash will become minus N dash. So I'm rotating my whole diagram by 180 degrees, okay, something like this. In that process, this circumcenter of my triangle will also get rotated onto the same line somewhere, right? So again, the whether that circumcenter lies on OH or not is not going to get affected by this operation. So therefore, I can freely multiply all my coordinates by -1 without changing the what we want it to prove. Okay. So therefore, I am in fact going to drop this minus sign also. Okay. So my new question is, consider triangle. Consider a triangle with vertices. So the first vertex is the circumcenter or the origin O, and the other two vertices are B times 1 plus 1 by C and C times 1 plus 1 by B. So these are the three vertices of this triangle. And my question is, where does its circumcenter lie? And very important, see, I don't care about the distance. I don't care how far the circumcenter is. I only care about the direction, right? As long as the direction matches the direction of OH, I'm satisfied. So ideally, what I would like to see is that the circumcenter expression is something like the coordinate of H times the real number. Okay? So if that circumcenter has this kind of expression, then I'm done. So I'm only going to compute the part which is relevant to the direction of the circumcenter. I don't even care about its distance. Okay. So now I just have to substitute the expression of circumcenter, because again, the fact that you have chosen the origin as one of the vertices means that we can directly apply the formula. Which formula? This formula. So this was the circumcenter that we got, right? If P and Q are my other two vertices, then the circumcenter is simply this one. And again here, see, that is why we observed that the denominator is a purely imaginary number. So it is already I times some real constant. So we don't even have to compute the denominator. We'll just say that it is I times some real number. Okay, so we'll focus on only the numerator, which is P into Q into P bar minus Q bar. Okay, so I can say that my circumcenter, so circumcenter O1, O1, it is small O1, so that is the coordinate, will be equal to, so instead of P and Q, I have this expression M and N, right? So M into N into M bar minus N bar upon some constant times I. This is what my circumcenter looks like. Let's compare it with my calculation to make sure I'm not making any mistake. Yes. So on the side, let us just compute M bar and N bar. So for M was, I just open the bracket, it is B plus B by C, and N was C plus C by B. So what will be the conjugate of M be? It will be term by term conjugate. So B bar plus B by C bar. And here again, we can exploit the fact that B and C are both of magnitude 1. So their product or the ratio will also be of magnitude 1. So again, it is simply going to be 1 by B plus C by B. It is just going to be the reciprocal of both. And similarly for N bar will be 1 by C plus B by C. Okay, I just have to take the reciprocal of both terms. So you see how it is very convenient that if you have all unit vectors, the conjugation is very nicely done. So we have everything to plug into this expression. So my O1 is turning out to be, so Mn, so B plus, uh, let me factorize this actually. So B into C plus 1 by C. So you see that some terms are going to get cancelled here, and inside I'm going to have m bar minus n bar, which is this 1 by b plus c by b minus 1 by c minus b by c, and upon some k times some I. Okay, so many things are going to cancel, and what will be this expression inside the bracket? Can we take the denominator? If I take the denominator of that, it is b plus 1 by c plus 1 upon this k times I into this c plus 1 times c minus b plus 1 times b. Okay, so I'll just rearrange, don't want to keep rewriting the left hand side part. So this is c square plus c minus b square minus b. And you see this can be factorized also, because I can see b minus c as a, or c minus b as one term. So c minus b times c plus b plus 1, right? That is how it can be factorized. And you see how very nicely what we were trying to reach is that this expression should be h times some real number. And what is h? H is simply 1 plus b plus c, right? So we are expecting this 1 plus b plus c as a factor to emerge at some point. And you see it has nicely come here. So now, so finally what I'm getting O1 is how much? B plus 1 times c plus 1 times c minus b upon some real constant times I into 1 plus b plus c. And we would like this to be some real times 1 plus b plus c. So therefore, what is the only thing left to be proven here? If I prove that this part is a real number, then I'm done. And there is already one copy of I in the denominator. So in other words, the numerator should be purely imaginary. Okay, so I would like to prove that the numerator of this expression, right? B plus 1, C plus 1, C minus B is purely imaginary. If that is true, then it will make dividing by I will make this number purely real, and therefore O1 will be exactly this the H scaled with some factor. Okay, but so how do you prove that a number is purely imaginary? In the diagram of a real plane, if there is a number z over here, which is perfectly along the y-axis, what property will that number have? What can you say about its conjugate? What can you say about its conjugate? If z is here, its mirror image z bar will be here, right? So what about z plus z bar? You see, if a number is purely imaginary, it has to be equal to negative of its conjugate. And this property is only true on this y-axis. Anywhere else you see, z plus z bar will give you the 2 times the real part. Okay. So I just have to compute that. So if I add this number to its own conjugate, and if I get 0, then that is what we need. So b plus 1, c plus 1 plus c minus b plus its own conjugate. Right. And so if I take the conjugate inside, so b bar plus 1, c bar plus 1, c bar minus b bar. And again, exploiting the fact that these are all magnitude vectors. So b bar will become 1 by b. and this will become 1 by C minus 1 by B. And you see what is happening now? If I simplify, see the first term will not change. The first term I'm not going to, I don't care about expanding. Actually, I don't need to expand also. If you see here what is happening, B plus 1 upon B, C plus 1 upon C. And see how nicely this was C minus B and this is B minus C. So, right? What happened? I made some mistake. I think I made a mistake somewhere. Just a minute. Right, sorry. This completely forgot. In this expression, this numerator we simplified as C plus 1, but we forgot that there's a 1 upon BC over here also. That 1 upon BC is still there. So I have to write that 1 upon BC everywhere. So in fact, I need to prove that this thing upon BC is the pure imaginary. Okay. So let me just delete and rewrite these lines. I have to show that this number is purely imaginary. Okay. Just make sure you mention that BC everywhere. Okay, so again, idea is the same. I'll just add it to its own conjugate. So let me just, instead of writing the conjugate every time, let me just compute its conjugate. So this is equal to, again, B bar plus 1, C bar plus 1. Yeah, and now this time you'll see that that term is going to cancel. Right? So the B bar C bar in the new denominator will become 1 by B, 1 by C, but in that process, they will be shift to the numerator. And now, so now this time everything is going to cancel. So BC will cancel with this. And so we will have, so you see how this, the conjugate of this, if I call this number Z, then the Z bar which I obtained is exactly equal to minus Z. The only term which has changed is B minus C has become C minus B. Therefore this number is purely imaginary. The numerator is purely imaginary. Therefore, that divided by I, that whole thing is purely real number. And so therefore we can say that O1 is just a scaling factor of scaled version of the orthocenter 1 plus B plus C. Okay. So I mean this may look like a lots of calculation, but if you think about it, we are just reusing some standard things. Like if I go all the way to the start of my proof, right? This is where we started, right? So if I just quickly recap what are the most important steps. So first thing we observed, by the way, I mean you may think that this is a lot of calculation, but understand that this was APMO question 4, and APMO Asia Pacific Mathematics Olympiad often has questions harder than IMO. So at that level, this much calculation is expected. But although there was a lot of calculation, we were somehow always simplifying the problem. So at every step, we had the feeling that we are simplifying the problem, not making it more complicated. So, like the very first step of simplification, that replacing this definition of that concyclic points with something which is easier to track in terms of the reflection. So the first step was getting rid of this concyclic expression and converting it to this reflection idea. Okay. Then the next important set of decision was choosing the right frame of reference, like choosing the circumcenter, circumradius, choosing the point A, so that I don't one more variable gets eliminated. So only B and C are my only unknowns, right? And then applying the reflection property that we found earlier to find the coordinate of point M and N. Okay. Then in that, see, leaving this H minus intact was an important step. somebody could easily expand this h as 1 plus b plus c and do some rearrangement. But in that, we lose the fact that we can use h as my pivot point to sort of move the whole diagram. You see how you have a control point that I can just move this point h to a different location, and along with that, my whole triangle gets shifted. And then I can again use that point to as the point of rotation so that my whole triangle gets rotated by 180 degrees. In that process, these terms get simplified. This so final the m which was originally given to us, and finally the m which we are using is much simplified without changing what we want to prove. We wanted to prove that the circumcenter lies on this line OH. So in this whole process, that circumcenter will still lie on the line OH. Okay. And so therefore we obtained this simplified version of m and n. And then the formula which we had derived earlier, again, how we cleverly ignore the denominator. We just say denominator is some real number into I, so that only the numerator had to be computed. And then finally, when we started to do the calculations, very nicely we got factorization that the numerator had this 1 plus b plus c term. And so we just isolated that in one direction and kept everything else aside. And so then finally this expression, if that is purely imaginary, then we are done. Okay, so I mean, don't focus on the calculation, focus on the strategy, that how at every point we are trying to make our life simple. So I mean, I don't even know the official solution of this question, that with pure geometry, how is this question supposed to be done? I don't know. I have some ideas, but I am not able to complete them. But that is what complex numbers allows you to do, that you don't have to worry about those details, but you have to pay the price. The price that you have to pay is that you have to be really good at calculation. So, I mean, just few last things. We have only 15 minutes left. Like, and as I said, that this is going to be the last lecture for now. So, what are the next steps for you? Like, if you want to become champion at complex numbers in geometry. So, I last time already said that I am Yaglom is one book. I think complex numbers and geometry in geometry, something like that. So that is one book where you will get a lot of these derivations, like how to find the reflection, how to find angle bisector, what is the condition where 4 points are cyclic. Those kinds of things are very nicely given in Jaglon's book. Then most important, develop your own systems. Okay. Okay. Develop your own shortcuts. Barycentric coordinates is an important topic which we could not cover today, but that there's a lot of importance to this topic actually. Interestingly, so you may know that I work at Nvidia, and Nvidia is all about 3D graphics, animations, things like that. uh, Surprisingly, barycentric coordinates is a very important what you can say aspect of all that theory. Okay, so we require to know some information about the vertex on the screen which we obtain in terms of barycentric coordinates. So it's a very interesting way of connecting with what I do actually. Sorry, something happened. Yeah. Okay. So barycentric coordinates is one more thing that you need to study in order to champion the complex number theory. Uh, what else? Yeah, I think pretty much those are the important things. I mean, one aspect where we have not really spent a lot of time in complex number is how we deal with circles. Like, um, there are the fact that if you have four cyclic points, not only what is the condition under which they are cyclic, but the fact that the angles can be related, right? This angle and this angle are supplementary and those kinds of things. So the out of how all of those things get translated in complex numbers is also important actually. And maybe a few other things I don't recall right now. But you have to do a lot of effort to become good at complex number. But the reward that you will get is that with almost 100% surety, every geometry problem can be tracked, right? I don't think that if there are, yeah, one important step is kind of identifying the right problem. Okay. Today my tablet is misbehaving. Identify the right problem. Right? Because you may have two or three more tools at your disposal. So at which problem is most suitable for complex number attack should be a conscious choice. That it is not that you have to do every problem with complex numbers only. Okay. And another important part is that you don't have to do complex number from the very start. Even in this problem, if you saw, right, when we started the proof, we first looked at the geometry. As much of simplification you can do with geometry, do that upfront. So first geometry to simplify the as much as possible. And the last step, so use complex numbers to evaluate. Okay. So if you do a good job of the simplification, then your calculation will automatically become simpler. Okay, so therefore this important step of simplification has to be started before you attack with complex numbers. And finally, I mean, this we have been harping all the way that what is this whole triangle of topics, right? Like complex numbers, geometric transformations. This the interaction between these two is very important. That the intuition of multiplying with a complex number is a spiral homothenity, conjugation is a reflection, and all these things. In fact, we have never talked about inversion, right? So inversion is one topic where it is also a kind of transformation, and that also has a its kind of image in the complex calculation. So this back and forth interaction is very useful, and always keep that in your mind. I think we have spent many lectures now dealing with transformations. So I think you have got a good amount of experience with that, that how you can interpret the complex numbers. So keep on developing on top of that. Okay. Okay, so I think that is all that I wanted to cover today. Anything else you want to ask, particularly for next Sunday's exam for INMO? I hope you are well prepared for that. You have got your admit card and whatever or any other logistic related help you require, let me know. But otherwise, maybe we'll have just one more session after the exam to discuss the paper, but I will keep that as optional. I'm not sure whether I will be able to do that or not. If possible, we'll have one session for that to discuss the INMO paper. But otherwise, I think this could be the last meeting for this academic year. Of course, you are always free to reach out to me over WhatsApp anytime you want. If you have any questions, you are solving something new, you discover something new, please share that with me, share that with everybody else also. So we'll keep interacting through the group and those kind of things. Uh, but yeah, that's all from me. Okay, thank you. Thank you. Bye.
Thank you, sir.
Bye, sir. Thank
Thank
you,
you, sir.
sir.
Bye.
Bye, sir. Thank you, sir.